The broadcast is now starting. All attendees are in listen-only mode.
All right, good evening, everyone. We're still going to wait a few minutes here to get started with the presentation. So the top of the hour, we'll get going. And welcome to the webinar. For those that just joined, we're going to get started here in a minute or two. Just wait until the top of the hour and then we'll get going. And welcome to the webinar. All right, so I've got 7 p.m. So we're gonna get started on our webinar with about the 2021-2022 winter weather outlook. So first, a couple of little housekeeping things on our end. If you go to our webpage at weather.gov/Boston/webinars, you can see the latest public webinars that are coming up. Now, there is one that is coming up soon that's not on the webpage yet, and that's going to be an event review of the tornadoes that occurred this past weekend, and overall what happened with the system as it was going through. And any of these recordings, if you've got to get going and can't stay through the whole thing, they are recorded and we do upload it to our YouTube channel, which is youtube.com/NWSBoston. And if you want to get an email update, if you don't look at the webpage, if you email Joseph Della Carpini, and you can see the email address listed there, he can, you can send him an email and he'll give you the webinar, a list for the webinar updates. And then also, if you've got any sort of suggestions or ideas for topics that we should cover, he's the person you can pass it along to, and we may do a future webinar based on the feedback that we get from you guys. So for tonight, here are the presenters for tonight's webinar. My name is Bill Leatham. I'm one of the meteorologists at the National Weather Service in Norton. I'm alongside here with my colleagues Rob Magnia and Rodney Chai, who are also both meteorologists at the National Weather Service. And so with that, I'm going to pass things along to Rob.
Thanks, Bill. Good evening, everyone. Thanks for coming. So we have a pretty big turnout tonight. So, we'll talk about the winter and what everyone can expect, at least in terms of temperature and precipitation. But before we get into the outlook for this season, I thought it would be nice to just talk a little bit about what's normal for Southern New England during the wintertime. So here we have these two charts for two of our local climate data sites in Worcester and Hartford. So the average temperatures in the wintertime in these locations kind of range from the mid 20s in January at the coldest to kind of the mid 30s in March and December, which are usually the warmer months of the wintertime. And that's Worcester being kind of on the cooler end of some of our local climate sites. For Hartford, Boston, and Providence, the temperatures tend to be a little bit warmer, with the average temperatures kind of in the upper 20s to low 30s in January and February, and then kind of in the low to mid 30s for March and December. You go to the next slide, Bill. And then just kind of showing this again for our other climate sites at Boston and Providence. You can see they're pretty similar as they are for Hartford, with the low temperatures, the average temperatures in January and February kind of in the low 30s, and then a bit warmer in March and December in the mid 30s. So as far as snowfall goes, Worcester tends to be our climate site that sees the most snowfall on a monthly basis, with Hartford coming in second, and then Providence and Boston. And we tend to see our most snowfall in the January and February months. And kind of from climate site to climate site, when you consider December through March as the months where we can get snowfall, occasionally you can get the late November, early April late snowstorm, but kind of including the months where we get the bulk of our snowfall in Boston and Hartford, our normal we see anywhere from 40 to 50 inches. Providence is a little bit lower, kind of in the 30 to 40 inch range, and Worcester, kind of being an elevated area out west, tends to see the most snowfall in the 60 to 70 inch range. So here's just kind of a summary of what happened last year for all of our climate sites. We see that the average temperatures were slightly above normal last year, and precipitation was generally slightly above normal for most of our sites, with the exception of Boston, which was slightly or right around normal. And the snowfall was pretty normal last year. And, it felt that way. We had a couple good storms, no real blockbusters. So you can kind of see the variability from site to site, with Hartford, Worcester, and Blue Hill being above normal, and then Providence and Boston being just slightly below normal. So it was a pretty normal year last year in terms of snowfall. And here's a table of some of the climate sites across the eastern United States. And these were the seasonal snowfall totals as of March 23rd. Again, you see last year Worcester kind of topped out for our climate sites, having 71 inches, which was about 7 inches above the normal of 64. And then Providence kind of being on the lower end with only 31 inches of snow last year. But again, that was pretty close to their normal of 33.9 inches. So a recap of last winter, if people kind of remember, we had a couple good snowstorms in December. So last December, we saw snowfall generally above normal for that month for each of our climate sites. And then January, things kind of turned down a little bit. Things kind of got quiet pretty quick. And then kind of late in the season in February, we had a couple good storms at the end of the season there. And really nothing occurred in the month of March, but you can go to the next slide, Bill. We'll show Hartford and Worcester. And then, kind of, just for the whole season, things were right around normal, with most of the action taking place in December and February, and we got that little break in January last year. So now we'll move on to the actual outlook for this winter. And so our colleagues at the Climate Prediction Center, the biggest predictor they use for the winter season is El Nino and La Nina. And that's because sea surface temperatures are reasonably easy to predict in the long term, as opposed to other weather variables. difficult to just forecast temperature and precipitation explicitly. But because it takes so long for the ocean to cool off or warm up, it's it's a lot easier to determine what the sea surface temperatures are going to be, and that's kind of what El Nino and La Nina revolves around. But it refers to the sea surface temperatures in the equatorial Pacific off the west coast of South America. So when you have above average sea surface temperatures in that area, we call that a La Nina pattern, and when you're below average, above average is El Nino, and below average is the La Nina pattern. And so for this winter, the Climate Prediction Center has issued a La Nina advisory. La Nina conditions are likely to continue through the Northern Hemisphere through this winter. They're giving it a 90% chance. So we'll see cooler than normal sea surface temperatures in the equatorial Pacific this winter, and we'll talk about how that might impact the winter here in the United States and in the Northeast. So again, so the way La Nina works, the global circulation has these the easterly trade winds at the equator, and when they strengthen, it pushes warm water at the top of the sea surface westward, and that warm water has to be replaced, right? So what happens is cold water comes up from beneath, and it steepens what's called the Equatorial Thermocline, which you can see in these figures here. So as the trade winds increase, you start to get cold water upwelling from the lower levels of the ocean, and that's what kind of gives us our cooler sea surface temperatures at the surface. So as a result, there is a tendency for blocking high pressure over the Pacific, and that can induce a jet stream pattern that is going to be favorable for kind of warmer and drier conditions across the southern tier of the United States, and also portions of the east and northeast coast, and cooler and wetter conditions for some areas in the northern plains and the Ohio River Valley, and occasionally in the Great Lakes region as well. So that's kind of what we're expecting to be the most likely flow regime as we're heading into this winter with La Nina. So here's a graphic showing the actual outlook for the winter for 2021. So right here we see the temperature outlook, and the shading in red are the areas where we're expecting above normal chance for temperatures to be above normal. So if you kind of look for most of the Northeast, we're kind of in a 40 to 50% chance that we'll see temperatures above normal. So not a huge signal, but we're definitely leaning towards having above normal temperatures this season, whereas the Pacific Northwest is expected to be below normal. And then looking at the precipitation looking at the precipitation outlook, as I mentioned, kind of during La Nina, you have a tendency to have wetter conditions across the Ohio River Valley and portions of the Midwest. And you see we're kind of just in the equal chances category, shaded in white in southern New England. So, we're just as likely to see above normal precipitation this year as we are to see below normal precipitation. So really the only area where we have confidence right now is that it might be a little bit warmer than usual this winter. And then we also have the 2021-2022 drought outlook for the winter. And we're kind of in the clear in that category, improved from where we were last year after that dry summer we had, not this past summer, but the one before that. So really nothing to worry about in that department if you live in southern New England. But unfortunately for portions of the western United States, they're expecting to either see drought develop or worsen, and maybe in the Pacific Northwest they get a little bit of an improvement. So I know a lot of people probably tuned in tonight to see what we were thinking for snowfall, but the fact is there's really no reliable methods for forecasting seasonal snowfall. The science just isn't there yet, so unfortunately we'll have to wait until we're a week out from that big snowstorm to really be able to give people the heads up. But I will mention, when we talk about these teleconnections like La Nina or El Nino, there's another one called the Madden Julian oscillation, and there's been some research that has shown that can influence snowfall in southern New England. But the Madden-Julian oscillation is only active when the La Nina is kind of in a neutral pattern or La Nina. And since we're expecting to be in a La Nina this winter, well, then there's going to be a chance for the Madden-Julian oscillation to become active and thereby maybe have the chance to influence either above normal or below normal snowfall in southern New England. So what is the Madden-Julian oscillation? So it's kind of this pulse of thunderstorms and showers that pops up over the Indian Ocean, and it moves eastward across the Indian Ocean, across the maritime continent, and into the Western Pacific over a period of 30 to 60 days. And then that area of convection kind of fades out over the Pacific, and then it pops up again over the Indian Ocean and recontinues. And again, this is active during La Nina and ENSO neutral conditions, and this oscillation could have impacts on the jet stream and storm tracks as well. So that's why we might keep an eye on this as we head into the winter. So taking a look here at each of these charts. So the Madden-Julian oscillation is kind of classified in phases, and each phase corresponds to where that area of showers and thunderstorms is located. So during the early phases, if you look on the left side of the graphic where you kind of see the green and the blue shading, that's kind of indicating rainfall anomalies. So in the early phases of the Madden-Julian oscillation, you see that convection and that rain kind of over the Indian Ocean, and then as you move forward, you start to see that area move eastward to the excuse me, across the maritime continent in the middle phases, and then eventually into the Western Pacific in the late phases. So this image on the right here is from a paper that was published a few years ago, kind of trying to relate different phases of the Madden-Julian oscillation to snowfall in southern New England. So they came up with some pretty good evidence that when the Madden-Julian oscillation is kind of in the late phases, 7 and 8 specifically, there's an increased probability of seeing snowfall in southern New England. So when you have that area of showers and convection with the MJO over the Western Pacific, there's a tendency for a greater chance of snowfall. But if the Madden-Julian oscillation is kind of in the middle phases at 4 and 5, they were able to find that kind of lowers the potential for snowfall. So this could be something we could use potentially as a predictor as we head into the winter. If we start to see the MJO being forecast to maybe get into phase 4 or 5, maybe we won't have to expect snowfall. But if once it gets to late phases, perhaps it might load the dice for a little bit more snowfall for our area. But again, that's something that can kind of only be predicted about 2 weeks out, exactly where the MJO is going to be. So kind of putting that theory to the test. If you remember back to 2014 and 2015, for those who were living in southern New England, that was the snowiest season that we had on record. And I forget what the exact number was for Boston. I know it was over 90 inches of snow that they had in a very short period of time. We had those 4 big snowstorms in late January and then a few in February. Madden-Julian oscillation was in phases 7 and 8 for most of that winter. So the figure we see from that paper verifies pretty well in this case. And then if we remember 2 winters ago, not last winter, but the winter before that, that was a pretty snowless winter. We didn't get a lot of snow at all. And kind of on the right, that those lines kind of show the path that the Madden-Julian oscillation took for that entire winter, and it spent a lot of time in phases 4 and 5, which from that paper, is kind of correspondent to a lower chance for snowfall. But kind of at the end of January there, it moved into phase 7 for a little bit. And if you look at that the chart in the bottom left, you see we had that little spike in snowfall in mid-January. So it appears that there's definitely a signal there that the location of the Madden-Julian oscillation can play a role in either stacking the deck for snowfall or stacking against the probability for snowfall. So that'll be something we'll keep a close eye on this winter, since it should be active with the forecast La Nina. And then looking at last year too, right? So putting it to the test again, we remember that things got kind of quiet in January after we had a couple of those storms in December. But January was largely quiet, not a lot of snowfall. Well, lo and behold, as we headed into late January, early February, the MJO got into the the late phases again, and we started to see that spike in snowfall where things kind of started to ramp up late. So three good examples there of how the theory from that research paper on the MJO has verified pretty well for southern New England, and having some predictability for chances above or below normal snowfall. All right, so now I think I'm gonna pass it on to Rodney. He'll talk a little bit more about La Nina and El Nino, and we'll go from there. Rodney, take it away.
Well, thank you, Rob. So as Rob mentioned, sea surface temperature near the tropics play a big role in our winter here in southern New England. And so the CPC has issued a La Nina advisory for this winter. So they're pretty confident that La Nina will persist through the entirety of winter, and in fact into part of spring next year. But the other question is, how strong will the La Nina be for this winter? And so this chart that you're seeing here, so basically on the left-hand side, it lists the winter seasons, which were influenced by El Nino, and on the right-hand side, the winters influenced by La Nina. And you can see that not all El Ninos and La Ninas are created equal, and these are the years that whereby there's an index called the ONI, and basically the ONI is used to classify the strength of El Nino and La Nina. And and again, as Rob mentioned, the winter of 2014-15, where Boston received the most amount of snowfall in a winter season, that was a weak El Nino year. And whereas some of the less prolific winters, like the past two winters, so if you take a look, 2020, 2011 was a moderate La Nina, and so if you go on to the next slide, so that again, that's the ONI, the Oceanic Nino Index from 1990 to present, and you can see that it's basically kind of like a continuum. So some of you who maybe remember 1997 to 98 was a strong El Nino year, and 2015-2016 was a strong La Nina. Strong El Nino year again. So how do you read this graph? So you have the horizontal axis at 0. Above that is El Nino, and below that is La Nina. And the more positive the value, the stronger the El Nino. The more negative the value, the stronger the La Nina. And so last winter was actually a moderate La Nina. And you can see that the ONI actually trended towards neutral, but then it dipped again. So that's why the CPC issued a La Nina advisory, because it's pretty much a lock that we're going to have La Nina. But is it going to be a weak? Is it going to be a moderate? Is it going to be a strong La Nina? The jury is still out, and I can tell you that the strength of the La Nina is going to affect how much snowfall, or at least it's part of the equation that affects how much snowfall we get here in southern New England. So we talked about the seasonal outlook, which from a forecasting standpoint, it's sometimes it's pretty much as good as a coin toss. But although the MJO that Rob talked about, that's actually one of the I guess our best attempts at conquering the seasonal forecasting frontier. But if you take a look at forget about forecasting 3 months in advance, but maybe just 2 weeks to 3 weeks in advance. That's when the NAO and PNA comes into play, and where they actually have quite a bit of skill actually in forecasting what's going to happen within the next 2 weeks. Maybe not down to exact how much snow does Worcester get, how much snow does Boston get, but it NAO PNA plays a big role in if you are a fan of the day 6 to 10 and day 8 to 14 CPC temperature and precipitation outlooks. These are the teleconnections that are used heavily by the CPC when they come out those kind of medium-term outlook. So if you take a look at from now through December 1st, notice that the NAO is going to turn sharply negative, and the PNA is going to kind of turn modestly positive. No, not very sharp, but it seems to be a positive trend. And when this happens, this kind of favors a trough over the eastern half of the country. And if you are a fan of cold weather or winter, you kind of want a combination of negative NAO and positive PNA. And again, the NAO stands for North Atlantic Oscillation, and the PNA stands for Pacific North American Pattern. So a positive PNA indicates ridging over the Northern Rockies, which plays a role in sharpening the trough over the eastern half of the country, therefore allowing colder Canadian air to come southward. And this combination again indicates the potential for enough cold, and assuming that we have the right storm track, we can get accumulating snowfall across parts of our area. The other thing that we like to look for is what we call the Greenland Block. So if you take a look at the the bottom figure, you see that those bright colors, the red, that represents higher than normal pressure, so high pressure over Greenland. And in contrast, there will be an area of low pressure off the Canadian Maritimes. So when this happens, we get a lot of our storms, a lot of the low pressure system riding up the eastern seaboard. And for people who love snow, so not only you need to have snow, have precipitation, but you also kind of need the storms to kind of be slow to move out to sea. And better still, you have a negatively tilted trough that kind of brings in the precip from into southern New England. So so a Greenland block is kind of like a very positive sign if you want to increase the odds of an intensifying system that is slow to pull away, because that increases the residence time of the storm, and in turn, given enough cold air, can give you more snowfall. So unsurprisingly, based on what we talked about, the CPC in its 8 to 14 day temperature outlook, so basically think, that's from Thanksgiving to December 1st, below normal temperatures are favored for much of the eastern US. And for precip wise, again, increased confidence for above normal precip. So we'll see if we start off the cold season with a bang. So this is the sea surface temperature anomaly, and you can see, what is very striking is La Nina is staring at us. You can see that in the Equatorial Pacific Ocean, the sea surface temperature are below normal, but 2 to 3 degrees below normal. So that's a classic signature of La Nina. But the other thing I want to bring to your attention is look at how warm the waters are off the East Coast, pretty much from, the mid-Atlantic seaboard into our coastal waters. So the waters it's been a very mild fall, and unsurprisingly, the ocean temperature are much warmer than normal, like 3 to 4 degrees above normal. And that is something that we will have to watch closely to see how much of an effect this would have on our early season winter storms. Because if the ocean temperature is too warm, you get a northeast wind. That's going to modify the air mass, and that could play a role in determining who gets rain, who gets snow, or who gets something in between. So we talked a lot about the teleconnections, MJO, La Nina, but at this point, we'll just go through some of the good old winter weather reminders, and the things that we look out for as forecasters when we forecast winter storms in southern New England. So the key ingredient or key benchmark that we look for as forecasters is what we call the 40° north, 70° west benchmark. Because if your low pressure system tracks in the vicinity of that benchmark, that increases the likelihood of seeing accumulating snowfall from the Providence to Boston corridor. And so in this case, if the low pressure system tracks too far offshore, it is outside of the benchmark, then pretty much the bulk of the precipitation is going to fall over the ocean. And if it is, if it is close to the benchmark, but outside of it, the South Coast, Cape Cod, and the islands might get heavy snow if the air mass is cold enough. But further inland, especially north and west of I-495 corridor, maybe just some snow showers or flurries. And then the sweet spot is it tracks over the benchmark. You can see the heavy snowfall, pretty much set up again right over the Providence to Boston corridor. And if you have the low pressure system kind of track over the Cape Cod Canal, you're pretty much going to get rain for much of southern New England with heavy snow confined to our north and west. So we a lot of us in the office are also weather enthusiasts, and we sometimes we like to look at the weather. I mean, we look at weather models every day, but sometimes we do like to look at what we call the fantasy runs, and like an example of a fantasy run is if you have like a blizzard, like the GFS shows a blizzard in hour 384, the question becomes, okay, that's kind of fun to look at, but then how much skew does, what is the probability of this becoming reality? The answer is very, very low. So, but we look at weather models. I mean, a lot of it is free on the web. But what exactly are weather models? If you take a look at the diagram on the right-hand side, you see a bunch of equations, and some of you who are more math savvy, basically weather models are solving a bunch of differential equations. But nowadays we have supercomputers that can process thousands of equations, because if you think about the atmosphere, you try to model the atmosphere. I mean, there's basically almost like a limitless number of variables, but you try to reduce it to maybe like 1,000 different variables, and then you have to solve, you have 1,000 different variables, you need to have 1,000 simultaneous equations. So if you take a human being to solve all these equations, you're going to take like months. But the supercomputer can do it in seconds. So that's the power of supercomputing. And nowadays we basically use numerical weather models, and the global models like GFS, they run 4 times a day, and different models, they have different resolutions, initial conditions, parameterizations, and that therefore you could have different kind of output. So I use the example of the fantasy blizzard in hour 384 for the GFS. But when I refer to that GFS, that is a deterministic model. So that's just one GFS member out of 21 different members. So the ensemble forecast basically, takes the mean of the 21 different members. And especially for, if you are so far out, 10 to 16 days out, the members are going to be kind of all over the place. And but as we get closer to an event, you expect this natural variability to reduce as they hone in on, hopefully hone in on one uniform solution. And that's when, our confidence is, is high enough for us to favor one solution over another. So, there are different ways to visualize the ensemble members. Another way is to look at the ensemble situational awareness table. And so you look on the left-hand side, you see each column represents a parameter. So the Z represents height field, T is temperature. You have the U and V wind, horizontal and vertical wind, sea surface pressure, and then the three right columns, those are the precipitation parameters. So we like to look, especially when we do the day 3 to 7 forecast, we like to look at this table and to see what kind of jumps out at us. And in this case, you can see, that's and this was from last year, actually, December 16 to 17. If you remember that we actually had a big nor'easter, and parts of the interior New England, they got 40 inches of snow, including Binghamton and southern New Hampshire. That was the storm. And you can see, anomalously high, precipitable water, or PWATs, and QPF, and as well as, anomalously high wind speed, especially north to south. So, you're jamming all this wind energy into a lower atmosphere. So given a cold enough atmospheric profile, you're going to produce prolific amount of snowfall. And that was what happened. So, just very briefly, global models include the GFS and the European model ECMWF, and you can take a look at the differences. GFS runs out to 384 hours. The EC runs out to 240 hours. And more global models are Canadian and UK Met. And again, you can see the differences between the two models. And again, as I alluded to earlier, how accurate is that model forecast beyond 3 days? Really, it's beyond 72 hours. The models are prone to large variation and errors. And you can see the average model error 72 hours out is over 150 miles. So, we talked about the benchmark, the 40-degree north, 70-degree west benchmark. 150 miles could make a difference between the low pressure tracking over Cape Cod Canal or tracking just outside the benchmark. So, kind of take your pick and have good luck forecasting that storm outside of 72 hours. And at this point, I will pass it on to Bill, who's going to take us to the end of the presentation.
All right, thank you very much, Rodney. So Rodney just talked about the global models, and now I'm going to talk about what are called mesoscale models, which is essentially we're looking at a smaller area. And the reason that we look at a smaller area with these models is it's really expensive computing time because they're run at a much higher resolution than the global models. So on the left-hand side is the NAM, which is a 12-kilometer resolution model, and you can see some of the other information on there. And then on the right-hand side is the nested NAM, which is a 3-kilometer resolution model that's also convection allowing. And then one other thing I didn't mention on that last slide that I should mention for these models is because they are run at such high resolutions, they are not run out anywhere near as far as the global models. The NAM, like we had in the previous slide, runs out to 84 hours. And with some of these models, because of how expensive they are to run and how long it takes to run, they only run them out for very short time frames. So the next model that we're talking about here is the HER, the high resolution rapid refresh. This model runs out to 18 hours. It's forecast 36 hours every 6 hours, and there's in between those 6-hour runs is when we have those 18-hour forecasts. And this is a 3-kilometer resolution model, as well as as we talked about before, the NAM 3-kilometer. So we kind of talked about ensemble forecast systems, and at least over the last couple of years, we've really started to hone in on trying to create a convection allowing ensemble model. And one of the models that we do that with is called the high resolution, the HREF model. Which is also 3 kilometers. It forecasts out anywhere from 30 to 48 hours, and you can see some of the other information on here as well. So what does the HREF contain? So it's 5 convection allowing models that are run together as an ensemble. And what it also does is it uses the most recent time run, and then the previous runs from those same models, and kind of combines them all together to iron out some different uncertainties, some different things that we're looking at. There's a lot of things that are going on in this chart above here, and some of these things that they're talking about are different. What Rodney had talked about, parameterization schemes, which are essentially trying to model things that are at a higher resolution than the model can run it at. Because once you get down to certain resolutions, there's some things that are going on at a much smaller scale than the model can resolve, and that's why they have to run these things to basically try to get an idea of what that phenomenon is doing. And again, this with the high resolution ensemble forecast system, it's designed to try to get at some of the smaller scale features. And when it comes to winter, it's snowfall bands, the coastal front, and then if you're talking with thunderstorms, getting into thunderstorms, what kind of thunderstorms we're going to get. That's some of the things that this model tries to help us do. So again, it's the HREF, which is what we refer to it as, the high resolution ensemble forecast. And here's an example of the ensemble mean or the maximum snowfall from the model, and it's basically a mean of all those 10 different models that we showed earlier. And you can see what this has for late March snowstorm in parts of New England. Another way that you can look at it is these postage stamps, which shows each of the individual members. So the one before is basically a combination of all of these different models, whereas you can actually look at each individual model to see if there's any differences amongst the models, amongst the individual models. And then we can also get into looking into snowfall amount probabilities. So this is basically showing where we have a 1 hour snowfall rate that's greater than or equal to 1 inch per hour. So that's when you're talking those really heavy snow bands. I think if folks haven't heard it before, they're called, usually we call them mesoscale snow bands. That's one of the things that you can look at. And then this other one is another snowfall rate probability, where this is, a really, really heavy snowfall, where you'd have 1 hour snowfall rates at or above 2 inches per hour. So just to go over some of the winter forecasting pitfalls, it's usually good, and this is something that we do at our office, is we rely on ensembles and probabilities, especially when you're beyond 3 days. Rodney kind of talked about that uncertainty, and there's also times where the models can kind of flip flop from run to run. We look a lot for trends and what models are doing, but you also, like it says here, there's from time to time where it can jump back and forth. Most winter storms aren't really predictable out more than 3 to 4 days ahead. As we kind of showed earlier with that low pressure center map, it's a really important to find the tracks of these systems. And if 3 to 4 days out, you saw that chart that we showed earlier with where the low pressure center could be. That has a big impact on if we're going to get snow and how much snowfall the region's going to get. But jet stream energy to help the storm doesn't usually come ashore the West Coast or the Arctic around that time frame. And with that, because the jet stream is offshore, we don't have the very helpful weather balloons that we launch getting into the models, because the jet stream at that time is over the ocean. And then one other thing, if you are a model enthusiast and you're looking at some of the different forecast models, when you're looking at a website, a lot of the time the model snowfall accumulation maps are using a straight 10-to-1 snow to liquid ratio, which doesn't account for sleet and also assumes an immediate accumulation. There's a lot of times when we have snowfall across this region where we don't get the 10-to-1 snowfall ratio, and it really depends on what kind of air mass we have in place over the region for what kind of snowfall ratio we're going to get, because there could be times where we even get snowfall ratios that are higher than 10-to-1. But again, if temperatures are near freezing, the model snowfall accumulation has to be taken with a huge grain of salt, which of course doesn't happen in southern New England ever, of course. But especially that will be somewhere where, especially along the coastline, since we're usually hovering right around freezing, that's where you could have a big pitfall with just taking the 10-to-1 snow to liquid ratio. However, the one thing that is good with this is it can show where the axis of heaviest snow, or even where the heaviest axis of precipitation would be, even if it isn't snowfall. So that's one of the benefits of looking at the 10-to-1 snow to liquid ratio maps. So what do we look at when we're trying to determine what type of precipitation is going to fall when we have a winter storm or some sort of system coming into the region? So this image here is showing basically the temperature profile as you go up in the atmosphere. And if you are below this black, if you were to the left of this black line here, that's when you have temperatures that are below freezing, or 0 Celsius, or also 32 degrees Fahrenheit. So when you're on the left-hand side, it's below freezing, and then when you're on the right-hand side, it's going to be warmer than freezing. So in this case, assuming we've got precipitation, what we would expect, because the temperature is all below freezing, that this precipitation would fall as snowfall. So things, however, can get dicey, where sometimes when you go higher up in the atmosphere, you get warmer air that punches in. And what can happen is when it's snowing in the higher levels of the atmosphere and this colder than freezing, it's falling as snow. However, it encounters this warm layer, and what happens is that snow starts to melt partially. And then in the lower levels of the atmosphere, it can be again cold enough for, and it's a pretty good deep cold layer. And those partially frozen drops refreeze and then become sleet. So this is when we would see sleet when we have a precipitation. And then when it comes to freezing rain, it's kind of similar to the sleet situation. The only difference is, again, at the top, we start off cold enough where it's snow. It falls into a very warm, a deep warm layer, as you can see with these temperatures going above freezing, and everything melts completely. And then we have a pretty shallow cold layer in the lower levels. And what happens is the raindrops become super cooled. And once they make contact with either the ground, a car surface, any kind of surface, it freezes instantly on contact. And then the one that we didn't show there, obviously, would be if we were expecting rainfall. That would be where if you had precipitation falling, even if it was as snow, if temperatures in the middle or lower levels went all above freezing, that's when you'd be expecting rainfall. And then this kind of covers all the last couple slides that I had, but just showing it all in one graphic. Again, the snow where all temperatures are at or below freezing, the sleet where you have it's starting off as snow, you have a little bit of a warm layer which does melt things partially, and then we have a cold enough layer that everything completely freezes and it falls, reaching the ground on contact. But it's since it's so cold, it's sleet. With freezing rain, again, you start off as snow. It warms up in the middle layers, a pretty deep warm layer, and then we have a cold layer at the surface. And once it makes contact, that's when you get we have the super cooled liquid water, which you would see, making really icy roadways. And then lastly, again, the rain. You start off as snow, but then you have warm layer all throughout the atmosphere, and then everything just falls as rain. So one of the other things that we look at when we're doing real-time analysis in the office of trying to determine what precipitation types are happening, one thing that we look at when we're looking at radar is something called correlation coefficient, or CC. And basically what it does is it's measuring the similarity of the precipitation droplets. So when we have a lower CC, a lower correlation coefficient, that's when we have a mixed range of precipitation types. There's a various amount of raindrops or drop sizes. And then also we have another thing, which would be non-meteorological echoes. However, when we go to the high correlation coefficient, which is going to values towards 1, that's saying that the precip it's the same precipitation type, and the particles or the drops are very similar sizes. So how does this work in a real-time scenario? So one thing that we look at is called the melting layer. There's a couple other ways that we can look at it, and you can see in the bottom right-hand corner here, we've got reflectivity, which is something you're probably used to. Differential reflectivity, which is this one on the top right, correlation coefficient in the bottom left, and then a specific differential phase in the bottom right-hand corner. So in the reflectivity, it's something that we've called as a bright band, which shows up, as you can see in this image here, a real bright ring around the radar. However, in this image, you can see that there's this really, it also shows up pretty well in the correlation coefficient. And what it's telling us is, and from that previous slide we went over, is, and we're going to use this big image here, which is, a similar situation. Within this ring of where the bright band is, we've got a large variety we've got not only snow, but we've also got snow changing into rain, and also rain droplets in this ring. And so we've got a lot of different types of precipitation, and also different sizes of precipitation, just because things are melting and other things are going on. Outside of this, where we have the values that are closer to 1, which is the darker pink. On the outside of this ring, that is all snow because there's a very small variety. Everything's very similar sized. And then inside the ring, you could also see, again, it's very uniform. And in that case, that's where we'd have the rain. So we do use this when we have a storm going on. You could see on both the image on the left, the loops on the left and the right, we can track the rain snow line with this specific thing. And you can see here we've got some snowfall reports being listed. Again, you see the rain snow line in the image here, and then to the right of the rain snow line, we've just got all rain. Now, one other thing that is really beneficial to us, it's always great to have what's going on the ground. And there is an application that you can download for free on the Apple or Google Play Store. It's called MPing, which is Meteorological Precipitation Identification Near the Ground. And this is actually something that researchers use to help improve some of the different radar products that we look at. But this is a way, if you want to get involved and tell us what's going on in your location, it is something that we see at our office, and if you travel across the country, any of the offices that you would be in would see what precipitation type you're seeing on the ground if you report it. And it's really, really useful information, especially when we have things transitioning from rain to snow, or in general, it's just really helpful to us. And then, with the winter coming up here, this is probably a good time to also go over some of some of the products that we put out. The one that's not listed here is the winter storm watch, and that would be where you would kind of be wanting to make the preparations ahead of like a winter storm. But a winter weather advisory is where we have dangerous weather expected in the next 12 to 36 hours. That's the one similar thing with all of these. That's all within roughly the next 12 to 36 hours. The only difference is it's basically a different level of impacts that are expected. When we have an advisory, travel difficulties are expected. So you kind of just have to, you have to be aware. When you get to the winter storm warning phase, that's where there's considerable travel problems expected within the next 12 to 36 hours. And it'll be dangerous winter weather. With the winter weather advisory, it's potentially dangerous. And then once we get to the blizzard warning phase, if we issue a blizzard warning, that's where we expect severe winter weather again in the next 12 to 36 hours. Or with all these cases, it could even be occurring. Now, with a blizzard warning, we're anticipating, if you see that's where we would be forecasting that there's going to be whiteout conditions. And it's really, if you see that, it's really probably a good idea not to travel. I'd say even with the winter storm, travel would be pretty, could be fairly difficult, and again, considerable travel problems. So that may even be an instance where it might not be great to travel. But with the blizzard warning, that's really when you want to, take action and not be heading out on the roadways. Another thing that you'll be on the lookout in the winter is there's these things that we issue now the snow squall warning. So what's a snow squall? It's kind of like it's basically like the thunderstorms for winter weather, which is we have really intense burst of snowfall and wind. It's a really short duration, but you can get that whiteout visibility because of how intense the winds and the snowfall is at the time as it's going through. And when that happens, you can have rapidly deteriorating road conditions, and you can kind of see, when it happens, you have people slowing down, and then there's sometimes where people are speeding up, and you can get accidents on highways. Now we issue snow squall warnings. They're issued when it's occurring or imminent, and it's usually in effect for 30 to 60 minutes. So it's kind of like the winter weather, like closer to like a severe thunderstorm warning, but with winter weather. When these are put out, it can be alerted on your phone. So if you are, on the roadways, you want to slow down, and again, because you were anticipating whiteout visibility or an intense snowfall, or if you're not heading out yet, maybe delay your heading out on the roadway. So what is a blizzard? We had gone over the blizzard warning, but what is it? So for a blizzard, it actually doesn't have anything to do with falling snow. It's not necessary for a blizzard. A blizzard can happen when you have blowing snow and 35 mile per hour or greater winds, and visibility less than or equal to a quarter mile, for at least 3 or more hours. Now, I know in central parts of the country, there's a phenomenon known as a ground blizzard. I know it doesn't happen too frequently out in New England, but you can have situations where you just had recent snowfall, and the winds are blowing strong enough that it breaks up that recently fallen snow, where you get something called a ground blizzard, where you get those blizzard conditions where the snow is blowing, you've got 35 mile an hour winds or greater, visibility is really poor, and it's for 3 or more hours. So just because it's called a blizzard, that doesn't necessarily mean it's from a snowstorm. It could be also from a strong wind storm going through the area from a recent snowfall that has happened. And then lastly, so this is something that we do internally with some of the local broadcast meteorologists, where we have a snowfall contest with each of the winters, or for the winter coming up. And basically what we all do is it's putting all what we think the snowfall is going to be at Boston from November 1st to April 15th at Boston, Providence, Hartford, and Worcester. And it's kind of more of it's really just for fun. But here you can kind of see what the average of the predictions between the forecasters at our office and the broadcast meteorologist that we've included, that, if you look for all of the locations, and you average all of our predictions, we're predicting below normal snowfall for all the locations, compared to climatology, which is in the blue. And then the median, which is kind of like what the middle of the pack values, again, that's still showing roughly below normal snowfall. The only one that's fairly close-ish to the normal would be for Providence. So with that, we really appreciate you attending this talk. Again, if you have any feedback, give an email to Joseph Della Carpini. And also, if you've got any ideas for future webinars, that would be the person to talk to, because he's the one that usually sets a lot of these up. However, we'll take a look at some questions here for a little bit and see what we can answer. All right, I'll let you guys also hop in here too, Rodney and Rob. See if we got anything. All right, sorry.
Hey, Bill. All right, so I see one at the bottom. I'll take a stab at it.
Okay.
This is from Tom Adams. If ENSO were weak El Nino and other oscillations unchanged, would this winter be similar to 2014 and 2015? So again, I'll just start to answer that one by saying there's really no reliable method to predict seasonal snowfall. But if you recall the discussion during the Madden-Julian oscillation, the Madden-Julian oscillation was active in that phase 7, 8 pattern, the Madden Julian oscillation was active and in phases 7 and 8 during a big chunk of that winter of 2014-2015, which that research kind of showed is favorable for increased snowfall. And again, we mentioned that the MJO is usually active during ENSO neutral or La Nina conditions. So I guess you could make the argument that the weak El Nino was kind of, close to that, to those neutral conditions. So it could have been that maybe it was the MJO kind of driving that winter. I can't say that with any high degree of confidence, but it's just the pattern that we saw. So it's and especially when you can consider 2014, 2015. I mean, it was almost a once in a lifetime kind of winter. So I wouldn't think that using any teleconnections like La Nina or El Nino would be a good predictor for having another winter like that.
All right, let's see. All right, well, another question from Tom, and I don't know if I could probably take this one. And so, Tom, we see your question. If not mistaken, Boston has had 6 straight above average temperature winters to date. Is this rare? So I'm gonna have to take a second here. I don't know. I'll let Rodney take a look and see if there's any questions that he can answer. But I'm gonna take a look at some of the data. But just on the top of the head, I mean, you can. It really just depends. It's really hard to say. I mean, I'm sure there's been times in the past where we've had, many winters in a row where we've had average temperatures above normal. It really is honestly just depends on what's happening through the winter during those years. But I could take a look, but I'm almost positive that we've had multiple winters in a row where we've had above average temperatures or even instances where there's been below average temperatures. But I'll take a look at some data here while we're looking at more questions.
Yeah, I'm going to answer the question by Kevin. So Kevin asked, does the NAO affect the amount of Arctic air that invades New England each winter? So if you want to, Kevin, if you want to look at, whether the Arctic air can infiltrate the mid-latitudes, you want to look at the Arctic Oscillation, so the AO. So when the AO is negative, it tends to, the Arctic jet stream weakens, and it allows Arctic air to dive southward. And sometimes people refer to that as polar vortex. So I would say you kind of need, ideally you need negative AO for the Arctic air to pour southward, but you also need negative NAO so that we have a trough over the eastern half of the country, because otherwise you would have the Arctic air pouring to the western half of the country if the NAO is positive. So yeah, I would say you kind of need negative NAO, but if you want to get the true Arctic air, you also need negative AO.
Okay, so we got a good one from Kevin Sheehan. I'll take a stab at. When did Ensemble models become a part of the forecaster's toolbox, and how does it play into forecasting winter storms? So that's a great question. I don't know exactly when Ensemble models kind of made their appearance. I know me, Rodney, and Bill all started school around the same time. My freshman year was at Plymouth State in 2009, and Ensemble models were around then. My guess would be sometime in the 2000s as like the evolution of more high performance computing is kind of evolved. You're going to need high performance computers to be able to make all those forecasts and the models. But as far as how it plays a role in forecasting, it's become huge recently. We use it quite a bit, especially with relationships between our emergency managers to communicate uncertainty and probabilities, because it really helps them make better decisions. So for example, if the European model, I think, has a 50-member ensemble, so if 40 of those models are showing greater than 4 inches of snow for the Boston metro area during the morning commute, we can tell them with a high degree of confidence, 80%, just based on the ensemble members, that there might be some impacts. And especially in the long term where forecasting gets difficult, I know Bill had mentioned that the further out we're looking, the harder it is to be accurate. So days kind of 3 through 7, we really rely on those ensemble models to get an idea of what's the most likely scenario. If we only relied on deterministic or a single forecast model in that time frame, I think our accuracy would be a lot less. So that's just a couple examples of how we'll use ensemble models in the forecasting process.
Let's see. So I see another interesting question from Kevin of, and maybe Rodney or I could probably answer this. How do forecasters tweak their forecast for the 40/70 benchmark? I don't know. You want to take that one, Rodney?
Yeah, sure, Bill. Yeah, that's another interesting question, Kevin. So as I mentioned in the presentation, the 40/70 benchmark is important because if the storm tracks in the vicinity of the benchmark, it increases the probability of the Providence Boston corridor seeing accumulating snowfall, assuming there is enough antecedent cold air in place. And I would like to tie it up with what Rob talked about for the previous question. So this is where ensemble forecasts play a big role, because if the GFS or the European model deterministic run, if it says, okay, like the low pressure is going to track near the benchmark, as a forecaster, I would like to see not just one member of a global model show that, but I want to see the majority of the ensemble members. And in the case of GFS, there's 21 members. I would like to see the majority of the members show a track near the benchmark. If it is all over the place, then that's a kind of a low confidence forecast, and that consequently decreases the confidence of us seeing accumulating snowfall in the Boston Providence corridor. So, in a nutshell, yes, we do. Our forecast is influenced by the benchmark, but I think more importantly, we kind of want to see the ensemble members kind of have some consistency and have some similarity before our confidence is increased.
All right. Since this is kind of part of your section, Rob, I think I'll toss this one to you. So, any signs the polar vortex will bring us frigid cold this winter?
So, I mean, I guess I would just kind of echo what Rodney discussed with the Arctic Oscillation and the North Atlantic Oscillation. The polar vortex is kind of, I always look at that as kind of like a hype word. It's just referring to that circulation over the poles. And when you have more intrusions of colder air, that's all the polar vortex is. It's basically just the polar jet stream, dipping farther south. And again, it's like Rodney had mentioned, the the Arctic Oscillation going negative is probably our best predictor in determining if we could have any cold air outbreaks associated with the polar vortex. And, at best, maybe we can get that kind of lead time in 2 weeks. Rodney had showed that graphic earlier for the latest predictions from the AO and the NAO, forecast to go negative. So maybe we'll get some cold air outbreaks in the next couple weeks. But, of course, it's still fairly early. We're still in the fall, so it might be another 4 to 6 weeks before using the Arctic Oscillation as a predictor for a frigid cold air outbreaks becomes more useful.
All right, we'll probably cover like maybe one or two more questions here. But and also to point out, Rob, like on that too, I know maybe this is what you were alluding to also, is the winter outlook from the Climate Prediction Center has this with the above normal favor for temperatures. And now just because we have that, it doesn't mean that we won't get cold air outbreaks. That's what they think is going to happen over an entire season. You can have weeks where you get colder air coming in and periods of cold. It's just when you average it out all over the season, they're anticipating it, the temperatures to be warmer than normal. Let's see. Well, another interesting one here, and whoever wants to chime in, why does Providence have the lowest average snowfall of the 4 climate sites?
Yeah, Bill, I think I would try take a bite at the question.
Sure.
It's a very interesting question, and in a way, it's personally, it sounds like it's a little bit intuitive as well, but then again, it's there's so many variables. So for everyone's benefit, we have 4 climate sites: Boston, Providence, Hartford, Connecticut, and then Worcester. So Worcester typically would usually get the most amount of snowfall. Not every year, but typically, because the site is located at 1,000 feet, so they do have the benefit of higher elevation. So and therefore, increasing the likelihood of more snowfall. Hartford, being in the Connecticut River Valley, it's more removed from the impact of the ocean. But then, if you get kind of like an inland runner, and when I say inland runner, it's like maybe a system, let's say if you get a low pressure system that tracks over the Cape Cod Canal, so well inside the benchmark. So places like Boston, Providence would be too warm. It would be rain. But Hartford, because it's further inland, it's kind of in the colder air, so it will snow. So Hartford, it can get quite a bit of snow as well. And then now we're left with Boston and Providence. So Boston, I would say it is not by much, but it's a little bit further north than Providence. So, that plays a role. But also, once you get past midwinter, especially when the ocean temperature has cooled, into the 30s, when you get a northeast wind, a nor'easter, you decrease the likelihood of the ocean temperature moderating the air mass. So, and typically, if you look at climatology, Boston gets most of its snow from late January onwards, as February is usually the snowiest month. So, so Providence being further away from the ocean, it's it kind of, I guess, gets less precip, given the same amount of same I guess thermal profile. So that's why it's not by much, but Providence tends to get less snow climatologically.
All right, Rodney, I got this. So there's two more questions here, and then we'll call it. And I'd also point out, if we don't get to your question and it's something that you really want answered, this would be where you could give Joe an email, and he might be able to answer any question, any burning questions you have. So one of the questions we had here is from Carrie. It says, with the combination of the negative NAO and positive PNA in a bomb cyclone type of snowstorm, do these conditions influence convective snowfall and the probability of thunder snow, which is Carrie's favorite winter weather phenomenon?
I'll take a stab at that one, Bill. So when we're talking about teleconnections like the NAO and the PNA, those really have the best utility for kind of just forecasting what a large scale flow regime is going to be. If we're going to have, troughiness over the East Coast and, potential for developing storms, or we're going to have a ridge over the East Coast, and is it going to be kind of dry? When you're talking about convection, that's, like teleconnections are kind of global scale, right? And we use them to predict synoptic scale, troughs and ridges. When you're talking about convection, you're talking about mesoscale, which is below synoptic scale, small thunderstorms. So it's probably not practical to try and use teleconnections to try and try and predict convective snowfall, because it's just so convective snowfall. It's just so small scale, and there's other things at work that you really need to be able to look at in the near term to make any predictability. I guess the only thing you could argue is for thunder snow, you're going to need those low pressure systems with warm sector, and as Rodney had alluded to earlier in the presentation, there is the potential with troughiness with a negative NAO and a positive PNA that you might have an increased probability of getting that low pressure system. So maybe indirectly there's a little bit of a tie there, but I don't think you could necessarily equate the potential for convective snowfall to simply a negative NAO and positive PNA flow regime.
All right, and then the last one I was going to go with here. So Tom, I see your question about, other than global models, what others are used. So we kind of talked about it, the mesoscale models or higher resolution forecast models. That would be the other set of models that we use as forecasters to, because this kind of ties into the previous question, to get into that, potential for like thunder snow, more into like convection and things that are going on at a higher resolution than the global models are able to predict, given given what the scale that they're forecasting on. So yeah, that would be the other set of models that we use, global models, and then you've got the global ensemble models, and also we've even got, we're starting to get more into the convective ensemble models. So there's a couple different things that we look at. So I think with that, we'll end the webinar here. But again, like I said, if you got any questions, give Joe Della Carpini, and I'm going to show it on the screen here again. Joe Della Carpini an email if there's any questions you really want answered. And again, thank you all for attending. And as a reminder, we'll be going over the most recent severe weather we had this past Saturday. We've got that event review coming up in early December. So hopefully we'll see you there.